Welcome to the Distinguished Lecture Series. I'm Karen Matthews of University Video Communications. Our program is designed to enrich graduate and upper division curricula with academic presentations by top computer scientists from industry. Its speakers and topics were nominated by computer science faculty of more than 50 universities. This presentation is sponsored by the Hewlett-Packard Company. Dr. Ira Goldstein, a major contributor to the development of artificial intelligence, computer science, and natural language processing, received his PhD in applied mathematics from the Massachusetts Institute of Technology in 1973. He taught at both MIT and Stanford, and in 1981, he joined Hewlett-Packard, where he is presently R&D Manager, Technical Systems Sector. His talk today is Natural Language Access to Databases. It's our pleasure to introduce Dr. Ira Goldstein. Ira?
The topic I'd like to talk about today is the processing of natural language by computers, one of the oldest and most challenging problems in computer science. That activity is often divided between speech processing and text processing. The focus I'd like to have today is on text processing, and in particular, I'd like to focus on natural language access to databases. The structure of my presentation has three parts. To begin with, I'd like to show why natural language is appealing, and in the context of this talk, to compare it to access to databases with formal languages. Then what I'd like to look at are some of the problems that natural language poses in this context and some of the solutions that have been employed. And finally, I'd like to turn to the problem of how to measure progress. So let's begin with the problem of why employ natural language at all to access information in databases. The first reason, as we'll see in a moment, is it actually turns out that natural language is a very efficient and terse way to access a database. Of course, it's also a very accessible technology, not requiring formal training in some arcane computer dialect. Third, natural language masks the internal and idiosyncratic structure of the database. And finally, natural language is designed to support dialogue, which arises naturally as you search for information on the computer. In order to illustrate some of these points, let's employ a simple database, in this case a database of individuals and items they've ordered from a co-op. Here you see a typical set of items that California folk eat. Now, if we look at this slide, what we see is an English query, very simple 6-word query: who ordered more granola than Robin? A burning question on the Stanford campus. Let's compare it to an SQL query. SQL is a formal language for accessing information in a relational database. It's an emerging standard in the field. And what you can see here is that the 6-word query becomes a 6-line SQL query, and not a query that one would ordinarily be able to articulate without some training. One can do a little bit better, but still remain formal. Here we have an example of query by example. You'll observe that the constants, Robin and granola, are simply typed into the table. Variables are entered by the user, in this case the variable y, and the operator to print the p period in the name column. This is a simpler way to do business, but it remains not very adequate when the queries become slightly more complex. Now, this too is a simple English sentence: which companies sell everything Tasty sells? But when you turn it into a formal query, whether query by example or the SQL code that you see here, it becomes very rapidly quite complex and easy to get wrong. It's also the case that natural language naturally supports dialogue. Here we have a question: which of the department managers submitted requisitions? We get back the appropriate table, and now a very natural thing to want to continue to do is to ask a question about that information. here were any of them for secretaries. Natural language with its pronominal reference and other devices is well designed for dialogue. Formal query languages much less so. This is not to say that there aren't advantages for formal query languages. First of all, they have a precise syntax and semantics. Secondly, they guarantee a kind of completeness for the information structures that they're accessing. And thirdly, they admit of a programmatic interface. They can be called by other programs. In fact, the natural language system that we'll be talking about is one that processes language and emits SQL queries. What I'd like to, on the other hand, there are disadvantages to formal queries. Formal queries, as we've seen, can become long and complex. Secondly, they require expertise on the part of the user, or more exactly, they require a database engineer between the real user and the computer. Thirdly, they require that that database engineer really understand the model employed to store the data in the computer. And finally, they're not nearly as cooperative as is natural language. This is typical of the natural language systems that exist today. It's a block diagram of the natural language server that we've built at Hewlett-Packard. And if you take a look at it, what you can see is that a natural language query comes into an application-independent core, which processes that English, applying knowledge of semantics and syntax, ultimately to produce a predicate logic expression. So it has made a step forward in the formalization of the user's input. That predicate logic then goes through a process whose output is a standard SQL query. The SQL query is handed off to a database system, and as this slide suggests, the database system can exist on an entirely separate computer. The database system creates a formal response, and you'll observe that there's an articulation component which takes that formal response and turns it into either the appropriate English or perhaps the appropriate graphic, picture, chart, or table. What I'd like to do now is to just give you a very brief indication of the system actually performing on the computer before we go into an analysis of the issues that natural language processing poses. What you see here is a typical screen provided by the workstation on which the natural language system runs. In the upper corner, you can see the query. In this case, the query is "Show me Starry Night." The database we're dealing with here is a database of Vincent van Gogh's paintings. In the other corner, you can see the parse tree faintly. This system is employed by researchers at HP Labs, not by end users, and hence the linguistic processing is revealed in one of the windows. And then in the middle of the screen, you can see the SQL query that has been generated in response to the English question. Let's now watch the system processing for a few seconds. This is actually real time. Here what you can see is the actual reply to the first question on the monitor in the upper corner. The system actually accesses a database, which in turn accesses a video disk, and Starry Night has been displayed. The next question is, in what period was it painted? You see pronominal reference for it, the parse, the SQL query, and now the answer coming back, Starry Night was painted in the Saint-Remy period. If only I could speak French. So that was just a brief presentation of the system to give you an indication that, at least in terms of the rate that it takes to process sentences, things are occurring in a real-time fashion. We do have to be cautious, however, about how well computers can do. Here we have a little cartoon where our user is asking which of my colleagues earns more than me, and the computer responds, Jones and Felon earn more. Well, so far, well within the capabilities that we've been describing. Unfortunately, people have a tendency to ascribe more intelligence to the computer than it deserves. Here we have our user going on and asking why those two earn more than he does. And of course, at that point, you're outside of the computer's competence. So one of the caveats is to make sure that as we make progress on natural language, we calibrate people properly for what computers can actually do. Of course, I suppose we do have the option of using an ELIZA-like technology and having the computer respond, well, does that bother you, obscuring the fact that it really doesn't know what's going on. Returning to some more serious topics, what I'd like to do now is consider the problems and the solutions that natural language processing poses. And before I do that, what I'd like to do is just mention the four constituent ingredients that any natural language system is made up of. First, of course, there's the lexicon or dictionary. And here you have that famous poem of Lewis Carroll's in which the grammar is correct, but the words aren't in anybody's lexicon, or at least weren't until he wrote the poem. Then, of course, there's grammar. Here we have meaningful words, but Shakespeare has been rearranged into a word salad. Then you can have words that have meaning arranged in a grammatical fashion, but still wind up with a sentence that's meaningless because the semantics are violated. Here's an example of Noam Chomsky's colorless green ideas sleep furiously. That is an example of that. And finally, of course, there's the issue of pragmatics, namely, you've understood the sentence, but do you do the right thing in response? We have a user inquiring, making the inquiry, do you know what time it is? And the computer kindly responding, yes, I do, but not bothering to tell that user what time it actually is. So these are the four ingredients that any natural language system must address. Now, the first problem in natural language processing that I want to talk about is the size of the lexicon that must be dealt with, and in fact the size, the number of utterances that must be handled. So to begin with, there are some 10,000 to 500,000 words, depending upon whether you're worried about reading a newspaper or counting all the words in the Oxford English Dictionary, and any of those words have, on the average, at least 4 forms. So you've got 40,000 to 2 million words. Those words, of course, are composed into sentences, which can be 10 to 20 words in length, but there isn't any absolute length on sentences, so we pick up quite a large number of utterances that we have to deal with. Those utterances are composed of hundreds of constructions, ranging from noun phrase and verb phrase to ones that delight linguists like hortative subjunctives. And the sentences, of course, can be paraphrased. So take a simple thought like list the managers of programmers and ask the question, well, how many ways could I say that and still be basically expressing the same thought? We puzzled about that question and actually worked on it a bit and found that it wasn't hard to get about 7,000 paraphrases of that simple thought. So natural languages are large also because of the many ways you can express the same thing. Now, how do you deal with that? I don't mean to suggest that because they're large, it's a problem that can't be handled. In the system we've built, and in a number of modern systems, a lexicon is built, an online dictionary, which has the appropriate knowledge represented in it. Let's consider the word have. Here's Webster's definition. And that definition, of course, has many lines in the dictionary and has some 16 meanings associated with it. So it's actually a fair amount of knowledge, although it isn't everything that a computer system has to know. If we take a look at the part of the representation that's actually employed on the computer, we observe here, first of all, that some of the knowledge is stored in a hierarchical representation. Have is a verb that is a member of a class. That's a subclass of transitive verbs. hence the slot parents. We also indicate various spellings, and in particular the third person singular of have is not haves, as my 2-year-old would say, but is has, and that exception has to be recorded as well. Semantics points off to an appropriate procedure, and the lexical rules here that apply to have are inherited from the superclasses, except that the passive is not typically used. We don't typically say Volvos or had by many Palo Altans. So the lexicon has the economy of a hierarchical representation, but also the ability to express exceptions. This illustrates the hierarchy in more detail. You see here the word have, as in does Ed have a PC, an instance of the class transitive, a class of verbs that need direct objects. That's a subclass of the class unsaturated, which in turn needs subjects, as in does Ed work at HP. The verb work requires a subject, but not a direct object. So, as in biology, one organizes the word classes into an appropriate hierarchy, grouping the description in a fashion that achieves economy. So the size of language is dealt in part by employing an online lexicon that uses structure sharing to minimize the amount of storage, but admits of fine-tuning and the marking of exceptions. Now, languages are also subtle. Let me take an example to show how easily one can have two rather different interpretations for only very slight differences in the sentence which is uttered. Here's a sentence which goes, list every manager of engineers who need orientation. Now, in this, with this sentence, it's the engineers who need orientation, and we're looking for managers of these engineers who need help. The parse of this sentence looks as follows, where the phrase who need orientation is a clause that applies to engineers. Now, if all we do is change one word in the sentence, and the sentence becomes list every manager of engineers who needs orientation, what we now have is a sentence in which we're talking about managers of engineers as opposed to managers of salespeople, and we want those managers who themselves need orientation. So we have two very different meanings to the sentence. There have been times in the history of natural language processing when some people have believed you could minimize the amount of grammatical knowledge and emphasize world knowledge and semantic knowledge. But I think as these sentences indicate, the grammatical knowledge certainly carries an important part of the meaning of the sentence. Not all, obviously, but it can't be ignored and needs to be dealt with carefully. And so this is the parse of that second meaning where the clause who needs orientation applies to manager, not to engineers. And here we have the two sentences contrasted with such a little difference, having such a big impact on its meaning. Now, the way to deal with these subtleties in language is in part to apply linguistic knowledge to the processing of the sentence. The linguistic knowledge for this sentence, which I think most of us know in one form or another, is that a sentence is composed of a noun phrase and a verb phrase, and they must have number agreement. One of the interesting things about the system that we've built is this rule isn't expressed explicitly, but rather is going to be obtained from a more schematic representation. What we have here, give me a moment before I show you that, what we have here is a list of the various grammatical areas that the system has to have some knowledge of. And now let me show you the schematic rule, which covers the noun phrase, verb phrase agreement, as well as a number of other structures. This rule is in a form and with terms you typically wouldn't recognize from high school. What it says is that if you have an entity called a head, which has a property of being unsaturated, and you add something called a complement, what you produce is an entity which now can be characterized as saturated. Well, those rather formal terms apply to the case we've just been talking about a sentence with a noun phrase and a verb phrase, but it also applies to building a noun phrase out of a noun and a noun phrase that is possessive, as in this case, Brown's job. And it applies to building a noun phrase out of a noun and a determiner. So in the line of work that we've been pursuing, we've represented a good deal of grammatical knowledge in a very schematic fashion, And surprisingly enough, we get a very broad coverage of English with only about 20 schematic rules. Of course, they expand into many particular rules as influenced by the lexicon, but the grammarian, the linguist, really only has 20 or so abstractions that he or she has to work with. And finally, I'd like to turn to the problem that natural languages are extendable. They're constantly growing. An example drawn from our computer world is reflected in these 4 sentences. It is not atypical to find nouns and verbs and adjectives and compound nouns all coming from computer jargon and flowing into common usage, at least in this particular community. And the issue here isn't whether they belong in the dictionary. The issue is that they have to be processed successfully if the natural language system is going to be useful to a particular user. Now, there are ways to deal with this. One can accommodate the application by actually looking at the database and at least drawing from that database a number of nouns. Here's a block diagram of what I'm suggesting. We have an application which may have terms in it like fuel line and filter. Let's imagine that's not already in our lexicon. What we can do is run a vocabulary extraction process that identifies some of these terms as nouns that may well appear in the user's utterances. Now, this obviously doesn't capture all the knowledge associated with filter and fuel lines, but it is helpful in the more constrained context of the user asking questions of a database which he knows to be about a certain set of concepts. So we have at least these 3 problems and these 3 ways of dealing with them that allow us to make a good deal of progress in processing language. But I'd be remiss if I didn't mention at least one 4th difficulty that natural language poses, and that is the ambiguity that is present there. First, there's the ambiguity in the lexicon. Words have many meanings. Here I've chosen the example manage. Which project does Jones manage? Did Jones manage to arrive on time? But as you know, a very large percentage of words have multiple meanings. If that wasn't enough, we also have to deal with the fact that structure can be ambiguous. Old orders and invoices might mean old orders and any kind of invoice, or it might be old orders and old invoices. Languages, of course, have ambiguity with respect to reference. When one says, who does he work for, one has to know more about the context in which that sentence is uttered to know the referent for he. There are ways to deal with ambiguity. There's context, there's inference, there's knowing the purpose of the speaker, and there's having common sense and world knowledge. And all systems today do some of this in order to resolve pronoun references. But this is really an open-ended area because taken in its entirety, the system is approximating human knowledge and human intelligence to really a large degree. It's for that reason that while we can make progress in applying natural language to particular situations, such as natural language applied to databases, we need to be pretty conservative about how long it will take to have a truly robust system that could satisfy the Turing test on an arbitrary topic of discourse. I'd now like to turn to my last point, which is how to measure progress in natural language processing. Obviously an important thing to do for a problem area as complex as this one. And I'd like to discuss 2 points. What are the dimensions that you measure, and then how do you go about measuring them? There are many dimensions with respect to measuring natural language systems. These are 5. How complete the system is, how confident we can be about one of its replies, how adaptable it is to new knowledge bases, how convenient is the reply, is it in the right form that we're looking for, and can the system be generalized to, for example, other languages. In the course of this lecture, I'd really only like to take a look at the first 2, completeness and confidence, although all 5 are important. With respect to completeness, there's the issue of the range of grammatical constructions, the size of the vocabulary. There's taking a look at completeness relative not to theoretically how many utterances there might be, but specifically what kinds of utterances are typically spoken or typed by users. And finally, there's completeness with respect to inference. Can the system deduce some of the obvious consequences of the facts that it knows? I think if you look at systems today, both in universities and in industry, what you'll find is that the systems are pretty complete with respect to the morphology of English, or the language that they work with. They're getting very good with syntax. Semantics and pragmatics, however, require more work, and I'm not sure there's any system that we can be entirely satisfied with. Notice I've indicated two levels of satisfaction. One extreme is human competence, and something more modest is product sufficiency. So there are a few successful natural language systems on the market which can be employed well if one knows the kind of information one's working with and is sensitive to the kinds of errors those systems make. Let's take a look at confidence. Confidence relates to both false positives and false negatives. A false positive and false negative would have to do with the system telling you something, asserting it's true and it isn't, or not telling you something that really is part of the answer to your question. Confidence can also arise from the system paraphrasing what you've said, so you have some idea whether it understood you even before you look at its answer. And there's the confidence that comes from the system making a mistake but being able to explain itself in a way that's helpful to you. There are some challenges here because there are systems that believe that simply spilling data at the user is an acceptable way to deal with false positives and false negatives. Let's look at an example. Suppose you say, list the equipment consultants have, and get back a table of the sort you have here, 2 consultants consulting for different areas with their respective equipment. So far, a simple sentence with a successful answer from a particular system we were actually looking at. On the other hand, if you just say list the equipment consultants, you get back exactly the same answer. Obviously, the system is doing a bit too much in the way of keyword analysis and a bit too little in the way of grammatical analysis. And here you've got a false positive, as Pollard is not an equipment consultant. Now, if you get back only 2 consultants, it's easy perhaps for you to take a look at it and figure out where the difficulty is. But if you're getting back a lot of data, or if the system is actually acting on the data, building a summary, or even worse, controlling some device, then false positives become completely unacceptable. Here's another example illustrating that as well. Is anyone a consultant and a manager? In the database, there might be no one who's a consultant and a manager at the same time, and yet there are systems who will simply give back to you all of the consultants in the fashion that you see here. Well, as you can see, natural language systems can misbehave with false positives and false negatives and no doubt even expletives deleted. Hence, it becomes very important for us to measure the performance of the system. Now, to do that, we'll need something to quantify, some set of test cases. The problem and the challenge with natural language is that it's hard to get that focused set of test cases. It's difficult to define a Michelson-Morley experiment, if you like. What we've tried to do to make some progress on this thorny question is to create a large test suite of sentences on a precisely defined database that has enough vocabulary for the test suite to be interesting, but not so much vocabulary that we can't make any progress on it at all. And so what we've done is we have built a database at Hewlett-Packard, a database now of sentences and of words and of construction types. And today it has about 200 construction types, about 500 words, and at the moment there are about 1,000 sentences, and we feel we need to go to about 10,000 in order to be able to measure a reasonable range of linguistic phenomena. Now, the linguistic phenomena all map into a relatively simple database. There's about 200 facts stored there, grouped together into about 20 frame-like structures, and that information, while not very large, does cover knowledge about quantification, predication, time, and location. So the database itself is really a kind that you would typically see in almost any database application, a database of employees with their jobs and their bosses and their ages and such. And what we do is we take our set of test sentences, now about 1,000, and run them against the database in an automated fashion, computing the number of parses for each sentence, looking at the answer extracted from the database based on the sentence, and seeing whether we've gotten both all of the legitimate parses, and for each parse, the accurate answer from the database. This has been important both to measure the current state of our system, as well as to see whether a change in a large and complex system like a natural language system actually results in the system overall improving in performance. This is a sample of the evaluation that we would obtain by running the current test suite of sentences. What it shows is that at least on the sentences we have put into the database, we're doing pretty well on relative clauses and questions and coordination. We're not doing so well on comparatives, and that, as a result, has become an area of focus for us. The system now has become large enough that the test suite is crucial because no single individual knows all of the modules that make up the system. So we've really moved from a world in which natural language processing could be developed as a single system by a single individual, really into the systems business, and we have to treat it in that fashion. So what I'd like to conclude with is, first of all, the remark that our measurement of natural language has both been valuable for assessing where our system is at, valuable for trying to compare our system with others to see how different theoretical approaches pay off, and valuable to inspire and direct the actual process of research itself. I think there's probably not been enough evaluation of natural language systems over the years, possibly because one can be somewhat hesitant to build test suites of 10,000 utterances. But I think it's important, and I think one has to step up to it. We at HP have been sharing our database with others in the field to encourage this process of evaluation. Our work so far has been focused on natural language in the context of English. We believe that the approach we've taken, and others believe that approaches they've taken, apply to other languages as well, although there has not been as much work as one would like taking the same theory and applying it to a diversity of languages. We think that's among the challenges to be undertaken in the next couple of years, and I think what we will learn about the generality of the linguistic theory based on that ought to be quite interesting. In conclusion, what I'd like to say is that natural language processing is challenging. In restricted contexts, it seems to be ready to provide a practical industrial solution, but for the general context, it really touches upon a very wide range of linguistic and cognitive phenomena. Using language is very close to what it is that makes us human, and we can't expect it to be a very simple thing to codify for the machine. Thus, it's my expectation that we will see progress step by step over the next decade, progress in both text and speech processing, but I don't expect that we will see an ultimate solution, a Turing equivalent natural language system, anytime soon. Thank you.
I'm Judith Lemon from University Video Communications, and our first question is from Boston University. Ira, what is the relationship between formal linguistic models and HP's work?
Well, the system that we've constructed does actually have a basis in formal linguistic theory. First of all, the syntactic part of the system is based originally on some work by Gerald Gazdar called Generalized Phrase-Structured Grammar. That was followed by an evolution done by Ivan Zog and Carl Pollard, and is in Pollard's thesis. And the work became head-driven phrase-structured grammars, which we particularly liked at HP because the initials went from GPSG to HPSG. It's also the case that the semantics has a formal basis. The system produces a predicate calculus representation based on Montague semantics, and then, of course, turns that into a formal relational algebra.
This question comes from the University of Pennsylvania. What is the future of speech input and output?
Well, I believe there's going to be a lot of progress in speech input over the next 10 years. I think computers have become powerful enough to do the signal processing at the initial part of the speech problem and powerful enough to do the semantic reasoning later on. I expect that we ought to see some really tremendous work out of Japan where the speech processing is linked to their text editing problem because there are so many characters in kanji. There's a lot of work there, and I'd expect to see results in the next couple of years.
Next question is a combination from questions raised by Stanford, UCLA, and the University of Pennsylvania. How much must we now and in the future depend on users knowing the structure of the database?
Well, I think it's fair to say that there is certainly going to be some dependency. I think natural language is becoming practical today where a user is interacting with a database whose content he knows a good deal about. Not the specific facts, but the kinds of information stored in the database. And I think it's going to be a long time before you can come up to a computer, ask a question on an arbitrary subject, and have it identify which database that information is in. I think that problem just opens up into a very broad cognitive problem.
Question number 4 comes from the University of Pennsylvania and the University of California, Los Angeles. To what degree can natural language processing be extended to real discourse?
Well, I think that's a very good question, because as soon as one sits down at a computer and types a sentence which is successfully understood, the next thing one does is type a sentence fragment which refers back to the previous one. We saw that in the talk where we had the example of which of the department managers submitted requisitions, followed by the question, were any of them for secretaries? I think that discourse is not as well developed in terms of its formal theory as is grammar and semantics, so there's more to be done there. There has been some work on discourse in the form of a theory called centering theory, and that is helpful, but there's more that needs to be done. As one opens up to discourse, one also opens up to the possibility of the system misunderstanding as well. For example, in the example I gave where the discourse went on to say, were any of them for secretaries, there could be contexts in which that wasn't referring to the requisitions being for secretaries, but for whether the managers were for secretaries. For instance, if the context was a debate in the company between whether managers should have administrative assistants or secretaries, asking whether any of them were for secretaries could mean something quite different. So we have to understand that we are making progress on discourse, but the more we ask of the systems, the more opportunities there are for the system to misunderstand. I might just conclude with noting that one thing you can do there is use paraphrase so that when the system attempts to understand a pronominal reference in the discourse, you can see whether it's understood it correctly by looking at the paraphrase it generates.
Thank you.
And our last question, can you comment on how to make progress on difficult topics such as natural language processing, especially in industry?
Well, I know there have been questions in other lectures in the series about research in industry, how it differs from academia, and how you pursue problems like this one that lasts really many years until you get a practical result. So I shan't go into the fact that in industry research is definitely a team sport, and that's part of the advantages of working in industry on problems that take a long time, that you do it cooperatively and you are past your thesis work, thank God. The element I would like to comment on is the need for a very careful evaluation theory to go along with any long-term research project. Otherwise, firstly, one doesn't have a very good way of convincing the people funding the work that one is making progress. When it's a multi-year effort, one really does need some way to address that. And secondly, as one builds large and complex systems with tens of thousands or hundreds of thousands of lines of code, theoretical progress on some particular issue may or may not result in the system behaving better or behaving with adequate performance. And consequently, I think one of the things we've learned over the years is that having a measurement suite that goes along with the building of the system is just absolutely crucial for success.
Thank you very much.
You're welcome.
Thank you entirely for your presentation.
Thank you.
And thank you for joining us today. We invite your comments and questions on this presentation, and we hope you will make nominations for future speakers and topics. If you are viewing this lecture on tape, there's a feedback postcard tucked under the label of your video cassette case. And if you're not viewing it on tape, our address is at the end of the credits. Thank you again.